In this hands-on, we'll cover data transformations with Python's map function. We'll explore the application of this function in various scenarios as before, these being streaming log processing, genome pattern detection, and stock price anomaly detection. We start with a simple example, extracting dates from log entries. Our sample consists of entries like info 2024 0110, followed by a string system started, and the same format for the second entry. Our aim with this task is to extract just the date component of the entry. We define a function called extractDate. It splits the log entry and retrieves the date. The map function is then used to apply this operation to each log entry in the list. And the beauty of the map function here is its ability to efficiently apply the same function across the iterable, in our case, our list of log entries. Our next task is generating complementary genetic sequences. Given sequences like ATCG, we need to replace each nucleotide with its complement. We start off with a few sample genetic sequences. The complement function performs this task of replacing nucleotides with its complement. The map function is then used to transform each sequence in our list. In our third example on stock price anomaly detection, here we're going to calculate daily price changes of stocks. Given two lists of stock prices, one from yesterday and one from today, we need to compute the change in prices. We'll use a lambda function with map to calculate the price change for each stock. Now that we've built your intuition around using map in this manner, let's now delve into more complex scenarios. In the first not-so-simple example on streaming log processing, we aim to analyze logs for error patterns and timestamps. Our log entries are a little more complex than before, including levels like error, warning, and timestamps. We have an extract details function here that's slightly more sophisticated than before, parsing each log entry to extract error messages with their timestamps. We then use map to apply this function, followed by filter to eliminate non-error logs. This illustrates map's integration with other functional programming constructs like filter that we'll cover in subsequent lectures and hands-ons in this course. For the second not-so-simple example in the realm of genome pattern recognition, we're now going to focus on detecting specific patterns or mutations in genetic sequences. We have a detect mutations function that identifies patterns in these sequences. As before, we'll use the map function to apply the detect mutations function to the list of sequences and subsequently print sequences and their corresponding mutations as a result. In the third not-so-simple example in stock price anomaly detection, we're going to perform slightly more advanced analysis to detect significant fluctuations in stock prices. We have a detect fluctuations method over here that identifies significant changes in stock prices. Again, as before, we'll use the map function to apply this function to the list of stock prices. And finally, print the list of fluctuations detected for each stock. In conclusion, as you've hopefully seen, Python's map function is a powerful tool for data transformation across various domains, these three domains just being examples to build your intuition and to demonstrate how they can be used in different ways, some simple, some not so simple. The important thing to note is that the map function allows for concise, readable, and efficient code to process datasets, making it a fairly important tool in your data analysis and functional programming toolbox in general. See you in the next lecture.